Swayam Prabha. Digital India. Educated India.
The commentary note is you're looking at p-small delta effects. You got a B1 that gives you a simple amplifier for the p-small delta effects. Is that larger than 1.2? If it is and it's connected to other members, you better start worrying about the the frame interaction there and the relative stiffnesses that are going on. I think you'll find that well, we're not going to be studying huge frames with Consteel, but we can analyze some. I've analyzed some very large bridge structures with Consteel, and it's quick. Yeah. So the problem with the computational tools is I think we're getting to the point where many times, well, how much time does it take to build the model? So that's some things where I think you'll find Consteel is very strong. You can build the model very, very effectively. The other aspects, you could argue for that, but remember that when we start a design, we're starting with nothing, right? And so until you've actually come up with member sizes, well, you could approximate, do some way of getting that and then analyze it. But when we do, these tools can be very helpful in terms of both kind of understanding where we are with some of the behavior, as well as when we're trying to do initial sizing of a structure. We don't have a specific frame to really do a very accurate analysis of yet, right? I did not find one with, but again, I decided it was best for me not to lecture you on, oh, this is what I'm seeing in the Indian code, but I'm thinking about some very specific things that are interesting aspects there. I probably won't remember them all correctly. There was one aspect in the Indian code, I believe it says that so there was an aspect there that, so you do a buckling analysis, or however you get your it's called the lambda critical in the Indian code. Is that greater than 5? And so the Indian code says, okay, if you're greater than 5 on your overall buckling, then don't worry about the sort of interaction we're talking about here, where you're getting differences in stiffness that are affecting your results. So that's how the code developers in the Indian code basically say, oh, here's how we can put a limit on that. So you could explore, okay, how do these relate? They're a little bit different. This is the way that the American code developers put some limits on. Okay, this is when you start to worry about you're not going to get a good result with your amplifier. I think I want to talk a little bit about one other aspect here with 1.3, and then we'll take. I want to talk about how we can use the amplifiers in a kind of a broader context when we're doing a second order analysis. And then I think we can use the time well to have, everybody has your computers, right? And so I want to try to get you in a good place where you're operational with Consteel. Okay, so the topic here is basically trying to illustrate it by this graphic. So suppose you're doing a geometric nonlinear analysis, or that's the finite element term, or second order analysis, or the design engineering term. And so you've got a discretization of the structure, and this is some element. You may be using some number of elements to model a particular member. But you're looking at the element level. You've got the nodes at the ends of the element for this frame member. The length of the element, I'm going to use script L to denote that wherever we're talking about an element length. So we've run our geometric nonlinear or second order analysis. We've got nodal moments, and let's suppose I'll show you some recommendations about how to make sure that your nodal moments are accurate in a second order analysis. So we followed those rules. We've got accurate nodal moments, but now, do we have a larger moment for the second order moment between the nodes? How do we estimate that? Now, if this, in a theory of elastic stability class, I could say, okay, here we can derive the differential equation solution, and yeah, we can calculate it. And but in a design engineering context, we're not going to do that. What are we going to do? The recommendation, we're going to come back to what I showed you in the topic 1.1. And so this often confuses my students at Georgia Tech. So we talk about, when we talked earlier, we say, we've got a member. So member length, capital L, right? And we've done a first order analysis, and so now, given your first order moments, let's estimate what are the second order moments in that member of length capital L. Let's what I'm trying to the concept I'm trying to pitch here is consider each element of your frame analysis. Okay, we're just going to isolate on that member, and we're going to assume that, let's put ourselves in a coordinate system that rotates with the member. And so we're just looking at what's going on there with that member, and it's a non-sway problem. And I say, my member is this element of length L. It's connected to other stuff, and so this is used a lot to basically make sure we cover the bases in American practice. The basis, apply the B1 amplifier there, given your second order moments, calculate a CM based on the moments in your element now, of script L length. You've got a P over PE script L, so that's just the length of the element. And that gives you an estimate of, if you're getting a number larger than 1 there, okay, I'm going to bump up my moments from what I've got from my second order analysis solution to cover what's going on in between the nodes of the element. Now for the calculation of C sub m here, if you don't have any transverse loads, we can use the 0.6 minus 0.4 m1 over m2 formula that I showed you earlier. Anything else, we just use C sub m equals 1, the general recommendation I showed you earlier. And this can be accurate for special cases. It can be conservative for a lot of situations, but typically the element length that we're exploring is not large, and we can live with this conservative approximation because often we'll find that the calculation here gives us a number less than 1 for B1. We take B1 equals 1. You can say you're treating each element like a member, like a braced member.
Member has only 1 element?
Well, that's in a lot of traditional work, we would often say, okay, we're going to use a single element for every member. And so then you've got to do this to...
Then I think this makes sense. But if you have
Right.
multiple elements per member,
multiple elements, it doesn't take much before you you don't need it. But that's where we're going. Right. That's where we're going next. There's a table that I referred you to earlier, but that was a table for either fixed or pin-fixed boundary conditions. Well, rarely are you going to have ideally fixed or pinned boundary conditions, so usually you're not going to use it. Now, a general recommendation, if you're a software provider or if you're writing your own software, is okay, I can handle this, and of course I could handle it by solving the governing differential equations and implementing that. But short of doing that, okay, for structural analysis, we need to ensure that the engineer is using enough elements to have an accurate nodal solution. And then once we have an accurate nodal solution, we would calculate just a first order estimate of the displacements relative to the chord there for our isolated element. So you've got your end moments that are coming from your geometric nonlinear analysis. You've got whatever internal forces are applied to your element. You just use a first order calculation, no p small delta, to get a delta first there between, and then, well, generally we need, even if we're doing a rigorous differential equation solution, we would, well, unless we're going to derive where the maximum is, we would have to sample. So we sample at close enough spacing of points so that P over PES, where S is the spacing of our sampling points, is less than 0.02. So PES being pi squared EI over S squared. And then from there, we calculate the second order, we had to calculate an estimate of the second order displacement as first order divided by 1 minus P over 4 PEL. Now, where's the 4 come from? What you can think of here is you've already solved for the nodal displacements or the nodal rotations relative to the chord at the ends of the element. So it's locked in that position. Now that you're treating everything as essentially a fixed solution relative to that, which then would have a K of 0.5, giving you a 4 times PEL. And once you have that delta second, you just use the fundamental calculation of M second is M naught, the first order solution between the nodes, plus P times delta second. And so this was kind of a student project in theory of elastic stability a number of years back at Georgia Tech. The student pretty much developed this approach and could show that doing it this way, we could hold the largest unconservative errors to 3%, and the largest conservative errors he was getting were 6% compared to the differential equation solution here. So that's a lot. That's a lot to get through. I probably confused you with what the heck is going on with this calculation. This is not a recommendation to a design engineer. This is a recommendation if you're a software provider. This is one way you could implement to do a calculation of what are the moments between the nodes. Has anybody implemented this? My student at Georgia Tech. If I talk to software providers, I don't know of anyone that does anything other than once you've got the second order moments, you just, if it's just end moments, for example, no transverse loading between the nodes, it's a line for the moment diagram between those end nodes. It's a first order approximation that's being used. And we'll see that in many situations, it's still good enough because we're going to use enough elements where it's not a problem. If you look at any software I know of, when they draw a moment diagram or when they give you moments at a given location, It can be accurate second order moments at the nodes, but then, okay, what is being drawn or provided for between the nodes, they're not including any p-small delta between the nodes. Okay? And it's not necessarily a problem.
So how many elements you need for this, for example, the 3?
Thank you. So a very simple rule that will keep you always out of having to hassle with all of this. Put in enough elements so P over PE script L is less than or equal to 0.02, okay? I'll have a slide later that shows what that means, but if you can think of, for example, if you've got a P over PE capital L for the whole member of 1, you put your 4 elements in there, okay, so divide that by 16, right? 4 squared. So it doesn't take much before then that wouldn't get you down to 0.02.
You want to go 1 by 50, so 7
Right, right. Now that's overkill for many types of elements, but that rule will give you something where you don't have to bother with having to fight with, I need to figure out some approximation between the nodes. I just use the first order approximation between the nodes. But also, we'll talk later about different types of frame elements. So one type is called a P large delta type frame element. And so for that one, this is a good rule of thumb to make sure that you get accurate nodal moments as well. If you have other types of frame elements, you don't need that many for accurate nodal moments, but this allows you to stay out of having to hassle with asking the question, do I have a larger moment between the nodes?